Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Alright, lecture 86, the wave equation. So this is going to be a little tricky to do because traditionally we use calculus to deal with these kind of issues, but we'll give it a try. And I want you to imagine, as we go through this, what I would like you to think of as waving is maybe a taut string. So imagine that I tie a string to the wall, I pull it taut, and I pluck it. Or better yet, if I wiggle one end up and down, right? Well, that's really going to be a standing wave, and we'll talk about those later. But today we're going to talk about traveling waves. So last time we talked about sinusoidal motion, so things that look like this. So last time we did things like y equals a times the cosine of omega t plus delta, right? And so we imagine that there's something, like say a mass on a spring or a pendulum, that is oscillating at frequency omega in time, okay? Today what we're going to do is we're going to think about waves that are spatially wave-like a water wave, but also move in time. So think of a water wave, right? It looks like a wave, like if you were to throw a rock into a pond, you see the ripples spreading out, right? Yeah. Those look like waves, little ripples in the water. But they also travel outwards, don't they? Yeah. So we're going to think of a wave. Does anyone have one of those little whiteboards? Yeah. So if I were to, put down my coordinate system and I say, well, this is some directional distance x, right? And this is y. That's the two spatial dimensions, right? And if I were to have a wave, let's say, initially at t equals 0, let's say it's here, right? And then we let the clock start running, and what does this wave do? It travels to the right. You see it? It's moving. It's a traveling wave. There it goes. Now it's gone. You understand the idea here? So not only is it at any moment in time, right, it's waving in the spatial dimension x, right? It's going up and down in y, yes? Yeah. So it looks like a wave in the spatial dimensions, but in time it's also waving, right? If you looked at a single point, right, in time, like say here at this time point, right? Where are we here? Well, we're like at this level here. As we move across here, it's going to go down, right? And then it's going to reach some minimum at some point down here, right? So it's going to oscillate up and down in time. So if we were to plot y versus t, what would we see? We would see it waving in time as well, you see? Yeah. So that is a traveling wave, okay? So we're going to try to understand these traveling waves. It will have a similar form to what we saw for simple harmonic motion, right, or oscillations. So it's going to have two parts. It's going to be a wave in space. So let's look at a wave in space, okay? Let's let y equal a times the cosine of kx. I'm not going to worry about the phase shift constant. Usually we put like a delta. I'm not going to worry about the delta, okay? So y equals kx, and if we were to graph that, what does it look like? Here's y, here's x. And you'll keep on going forever, right? But here we have this point a, right? At x equals 0, right? This is maximized, so we have a value of a, right? Later on at x equal, when the argument of the cosine is at 2 pi, will be at 0, it will be at a again, right? So we call this distance here the wavelength lambda, okay? And how does that relate to this k? Well, this k, right down here, k is equal to 2 pi divided by lambda. So whenever we get to this point, so at x equals 0, obviously the magnitude of this wave is a, right? But what about when we get here? What is this x value here? Okay? Well, if this x value is lambda, right, and we multiply that times this k, which is 2 pi over lambda, right, the lambdas cancel and we just get 2 pi, and so we have amplitude a again. You see? Yeah. That's all it's doing. It's mapping spatial dimensions to radians, right? Degrees of rotation, right? Which this cosine takes as an argument, okay?
Okay.
So that's the spatial part. What about the temporal part? Well, here we're going to write something that's like this. T. Y equals A times the cosine of omega t. Okay?
All right.
So what's this look like? Well, actually, it's very similar. It's almost identical, except this axis is t. This axis is still y. This will be A again, okay? But we're going to call this distance from peak to peak, just like we did over here. We called it the wavelength, right? That's the distance between two crests.
Yeah.
It could also be the distance between two valleys, if we had two valleys in here, right? Troughs, I think they call it in waves. This is going to be called the period. And it should remind you of the pendulum, the period of the pendulum, right? As the pendulum oscillated, it started its oscillation, then it came back. The time it took to make one oscillation, we call the period of the pendulum. Yes?
Yes.
So it's the same idea here, but it's also the same idea as this, right? We need to get this cosine function to take an argument that when t is equal to 0, it gives it an amplitude of A, but also when it's at whatever this time is, right? This would be the time big T, right, for one period, needs to be 2 pi. So that means that omega also has to be related to radians, and it's done like this. It's 2 pi over t, okay?
Yeah.
So that way, when I'm at time t, the argument of this function, right, will become 2 pi, so that I'll get A as my value, yes?
Yes.
Does that make sense?
Yeah.
So if the time t is big T, one period, then big T times omega, which is 2 pi over big T, is just 2 pi, right?
Yeah.
Because the big T and the big T's cancel, yes?
Yes.
Do you see that or no? I mean, I can put it in explicitly, right? I can say, okay, let's y at time big T would be equal to A times the cosine of omega big T, but omega is just 2 pi over big T times big T. The T's cancel, we get cosine of 2 pi, which is 1, right?
Yes.
So we get the correct amplitude again. Does that make sense?
Yes.
So here's the picture for space, here's the picture for time, okay?
All right.
Now let's talk about how to make a wave travel. Let me write down this result over here. So omega is equal to 2 pi over t, and k is equal to 2 pi over lambda. K, by the way, they call it a wave vector. Now here it's not really a vector because we only have one spatial dimension that we're waving in, right? But if we were to describe a three-dimensional wave, a wave propagating in three-dimensional space, then the wave vector would have components in all three spatial directions, okay? Hence, wave vector. Okay, so how do we make a wave travel? First, let's review the following. If I write that f of x is equal to x squared, yes?
Yes.
And what does the graph of that look like? Here we'll call this f, we'll call this x. We know that this, of course, is a parabola, right?
Yeah.
Whose vertex is at 0, 0. Yes?
Yes.
What about f of x minus x naught? Right? Obviously, the form of that equation is going to be x minus x naught squared, but we know from algebra that we don't have to really fuss with this too much, right? Because we know that what this means is that there's going to be some value, x naught, right? And all we're going to do is move the vertex of this parabola to that point, right? Who remembers this from algebra? Because it says, okay, well, I want to think of using this graph to make this graph. So I say, well, when I'm at x, when x is equal to x naught,
Yeah.
right? That's x naught minus x naught, that's 0, right? So that's just like what we had over here, right? For f of x is 0 when x was equal to 0, right? So this graph is just this graph moved to the right, to the point x naught, where the vertex is now at x naught. Yes?
Yes.
You guys remember that? So we would write that f of x and f of x minus x naught, this is just a shift to the right. If it was f of x plus x naught, that would be a shift to the left. Yes?
Yes.
If we wanted to shift it up or down, all we have to do is just write it as f of x plus some, y. If I want to move it up, I'd say, well, this would just be f of x plus some y naught value. That would move it up. So the vertex was now at y naught. Right?
Yeah.
If I want to move it down, I'd subtract y naught, right? So this is just, function notation, moving graphs around through translation. Yes? You remember that?
Yeah.
Okay, well, so that's what we're going to do here, okay? So here's what our equation will look like for for waving in both space and time. I'm going to write that f of x is equal to, actually, let's just write it as y, just like we did before. Y is equal to a times the cosine of kx minus omega t. So this is just a graph of a cosine kx, and then we can shift it. As time goes forward, we're moving it to the right, you see?
Yeah.
So that's all it is. So this is the form for a traveling wave, okay? So let's look at the argument of this function and what it does, okay? So if I wanted to, I could call this quantity here theta, right? It's a function of x and a function of t, yes?
Yeah.
What does theta look like? Well, I'm not going to necessarily graph theta, but I want to write out the relationship between these two things, right? So we have x, let's do t. Where do we want to put t? Normally we'd put t like this in relativity, and we put space over here, right? But this time I'm going to do it different. I'm going to do it as t over here and x over here, okay? So, for example, what about theta equals 0, right? If theta of x and t equals 0, what does that mean about this? That means that kx minus omega t equals 0, yes?
Yeah.
Which means that kx equals omega t, which says that x is equal to omega over k times t. Yes?
Yes.
You got that?
Yeah.
So that's this point here. It's just a line, right? This is just the equation of a line with slope omega over k, right?
Yeah.
Where this distance and this distance, what are these given by? Well, remember our definitions for this, right? So omega is 2 pi over t, and k is 2 pi over lambda. The 2 pi's cancel, right? So we can also write this as x equals lambda over t times t, little t, right?
Yeah.
So that means that the slope of this guy is given by the rise is lambda, right? The wavelength. The run for the slope is the period t, yes?
Yes.
But let's think about it another way, right? What does this represent, right? So this is just at one particular time, right? For one particular point on the wave. This is the point on the wave where the argument is 0, yes?
Yeah.
I could simply add 2 pi to this and that would be true as well, right?
Yes.
I could track any other point that I wanted to, but here I'm really tracking kind of the origin of this graph, right? So if I were to draw the y versus x graph, right? It's a cosine, so it's going to look like this. I'll just draw one period of it, right? There we go. When theta is 0, right, we can think of that as being x equals 0 and t equals 0. That would certainly give us 0, right?
Yeah.
So it's this point here, right? So what is this graph telling us? Well, this graph is telling us how this point moves, okay?
All right.
And x equals something times t, all right? Distance equals something times time. What do we call such a something? If I have a time and I want to convert that to a distance, what do I usually multiply it by? If I want to know how far my car goes, speed, right? Yes. So this term, omega over k, or lambda over t, right? Lambda over t, look at it. That's distance divided by time. That's a speed, right? So we call this the wave speed, okay? X equals v times t. That's the wave speed, okay?
Okay.
Because waves are a funny thing. So what is it that's moving, right? It's not material that's moving. We don't move matter necessarily. It's moving up and down, yes, but it's not traveling. There's no matter traveling to the right. What's traveling is energy and momentum, I suppose, right? It's the transference. A wave is simply the transference of energy and momentum in time and space, okay?
Okay.
It's not moving matter. Usually when we talk about velocity, we talk about, well, we're moving something, like a block, right? Or the mass on the spring. It's moving to the left, and it's moving to the right. And it's moving to the left, and then it's moving to the right. Yes?
Yes.
Here we're talking about the transference of energy, okay? So like when you see a water wave, right? That water wave, if you were to have you ever looked at a water wave on, say, a lake, or maybe you're on a lake that has lily pads, right?
Yeah.
And they float on top of the water, right? When the wave goes by, the lily pad rises and then it falls, but it doesn't move, right?
Yes.
I mean, it's not the water that's moving, right, when it waves. it's just going up and down. So what is it that's moving? You see something moving, right? I throw the rock in the pond, I see something moving outwards, but it's not water. Water isn't like moving from where the rock fell and leaving a hole. You don't like have a permanent hole in the water there, right?
Yeah.
Yes? Does that make sense?
Yeah.
So it's just energy and momentum that's being transferred. And so that's what a wave is, right? Does that make sense?
Yeah.
It's a little hard to wrap your head around, I suppose, the first time you think about it. But that's what it is. And this is the wave speed. So it's the speed at which energy and momentum are being transported, right, in space and time. Okay? If we were to, like, when I held up the whiteboard before, I had the wave, right, moving. That's what's moving, right? But the matter is just going up and down, right, if it was a string, right? So let me write this down. The wave speed, W, is, V, is equal to omega over K. All right?
Yeah.
Does that make sense?
Yes.
Okay. I know it's not easy, but... Okay, for the next thing that I'm going to discuss with this, what we're working up towards is something called a wave equation, okay? And it is applicable for all, well, it's what defines a wave. It is the thing that makes waves, right? And we can use it to figure out waves in, say, like light waves, water waves, sound waves, strings waving, okay?
Okay.
But there's some notational funniness that I have to deal with here. And so what I want to do is just real quickly introduce some notation, okay? So if I have a line, let's say, right? Let's call this y and x, yes?
Yeah.
A tangent, right, to this line. If we want to think of this as, no, I don't want to do velocity. Well, actually, let's do velocity. That's good. Here's t, yes?
Yeah.
So we'll call this x. So distance, time, right? This is something moving at a constant velocity, right? How do we know that it's a line, right? And so what is its velocity? Well, we just pick some starting point, let's call it 0, and then some finishing point, we'll call it, I don't know, just call it t, right, in time, and it finishes at x in time, right, for space. Its velocity is, the delta x over the delta t, right? Delta x over delta t, yes?
Yeah.
And that is just a line, right? It's just it's this slope right here, right? So we can draw a line like this and say that's the velocity vector, okay? What if it wasn't a straight line, though? So it wasn't so clear like this, right? Could be something like this, let's say. I'm going to think of the simple motion, right? If I throw a ball, right, or I drop a ball, right? So we have a constant acceleration, and the consequence of that, if you recall, is that the distance versus time, it looks like a parabola. So it looks like this, right? And so I have to pick a point and ask, well, what's the velocity here? And it ends up being this, like, if I want to know what the velocity is here, it's this tangent line. Do you remember that?
Yeah.
And so how do I get that? Well, I need to consider a couple of points. I could, for example, start with, say, this point and say this point, and I make a line that goes through the two of them, right?
Yeah.
I think they call that a cosecant line. Or is it a cotangent line? I can never remember. But anyway, that's the average velocity between those 2 points, right? Because we'll have this point here and this point here, right? This is a delta x, this is a delta t, this is my average velocity. And I allow these 2 points to get closer and closer and closer to this point that I'm really interested in. I want to know the instantaneous velocity here, right?
Yeah.
And so we find the instantaneous velocity ends up being, for a parabola anyhow, if I look at v versus t, that ends up being a line, right? Constant velocity, constant acceleration. Do you remember that?
Yeah.
So now I've got v and t. If I look at the delta t, delta v, right, this was our acceleration, right? Delta v over delta t, yes?
Yeah.
So here's where I want to introduce the funny notation. Instead of writing it as delta v over delta t, right, I want to write v. So here we've got x versus t, and we call the velocity this delta x over delta t, okay?
All right.
But I can do, so in calculus we take derivatives. This would be the first derivative of position. This would be the second derivative of position, okay? So what is delta v over here, right? Well, let's just rewrite this as delta v. Delta v is delta x over delta t, right?
Yeah.
So this is delta x over delta t over delta t. Yes?
Yeah.
So the notation I want to introduce, right, is that this will be the same as it always has been, just delta x over delta t. But this, the thing that when we talk about constant acceleration or with the regular kind of kinematics problems that we did at the beginning of this class, right, we would call it acceleration. We're going to write it like this: delta 2x over delta t squared. Do you see why? You see we've got two delta t's in the denominator, right? So they'll be delta t squared, but we really only have the one delta x here. But the 2 means that I've kind of done this operation where I find this thing in calculus, we'll call it a derivative, right? I find a tangent line to this curve, okay? And then I find another tangent line to the curve that describes, you see?
Yeah.
So it's doing this operation twice, finding the tangent line. First to this curve, then to this curve, the velocity versus time, okay?
Okay.
So what we call the acceleration, we're going to call it delta squared, delta t squared, okay?
All right.
Does that make sense? Notice that the 2, the square, is not on the x, right? This is not delta x squared over delta t squared, okay?
All right.
So that's the bit of notational funniness that I wanted to try to make you understand what I mean when I write it. Do you understand it here? It just means this is the acceleration, okay? Yeah?
Yeah.
And this is how we get that, right? So we would then graph the acceleration. It's just a constant, right? This is just a constant slope because it's a line, right?
Yeah.
Make sense?
Yes.
Okay. Okay, so let me write the wave equation again. Y equals a cosine kx minus omega t. Yes?
Yeah.
This is what we talked about before. This is our traveling wave, right? Just looks like a cosine function that as time goes on, it travels to the right. Okay?
Okay.
But how would I change this? How would I change this if I wanted to make it travel to the left? You want to see what I would do there? If instead of traveling to the right, I want to make it travel to the left? You want to see the simple thing we have to do?
Change the minus to a plus.
Yeah, we change the sign of this, right?
Yes.
Now we make it travel the other way. Good. So first I want to consider a point on this graph, a constant x position on this graph, and follow it. Okay? So this is for constant x, and we'll just call that point x naught. Okay, so now the equation of interest is y equals a cosine k x naught minus omega t. So this term is not changing at all. This term is. Okay? And remember the stuff that we did when we tried to get the velocity for the simple harmonic motion, when we looked at the cosine wave and we said, well, here it starts out, we find the velocity, the tangent line is sloping downward, so it's negative. And we see that the pendulum is, when it reaches its maximum amplitude, its velocity is 0, and then it starts accelerating in the other direction, getting faster and faster, and reaches its maximum velocity when it's straight up and down, the angle is 0, right?
Yeah.
Or if it was the mass on the spring, when we're at the equilibrium position, right, of the spring, there are no forces, right? The velocity is maximized. Remember, the spring always resists motion, right? So if I'm at the equilibrium position, there is no resistance to motion. My velocity is maximized. And then I start compressing, and the spring pushes back and slows me down, right? And I eventually get to minus a, right?
Yeah.
Where my velocity is again 0, and now I reverse direction and go back, right? And we looked at the tangent lines on those on the cosine function, right? To reason through what the velocity would look like, right? So here, what I'm going to do, instead of writing velocity, I'm going to write delta y over delta t, because I have x fixed, right? So this is looking at this point in time. So this is equivalent to a velocity in kind of the up and down direction, right? But I'm just going to write it as delta y over delta t, and just based on the analogy that we did last time, I'm just going to write this as minus a. Remember that we would have whatever was in front of the space or time variable, we just multiply that through by it, right? So minus omega times minus makes it positive. We get an omega here, and then we get our cosine function back. Cosine of kx naught minus omega t. Yes?
Yeah.
And then we wanted to get the acceleration, right? So we took another, we looked at what the slope of that was doing, right? Actually, I don't remember if we did do that. Yes, we did. We looked at the acceleration component by doing this process again, right? And looking how, oh, sorry, this is not a cosine, this is a sine now. My bad. We did the same thing that we did before, but for a sine wave this time, right? And we would have written this as acceleration, but this time I'm going to write it, like I showed you just a minute ago, as delta 2y over delta t squared, right?
Yeah.
This is just this, delta y over delta t, all over delta t again, yes?
Yeah.
And so what's that going to give me? Well, now I've got this factor minus omega I'm going to pull out again, so that's going to make it minus a, but I already had an omega here, so it becomes omega squared. And the sign turns back to a cosine again, right? Kx naught minus omega t, yes?
Yeah.
But this is just equal to minus a omega squared times y, right? Yes?
Yes.
Similarly, if I consider constant time, so I look at just one moment in time, and now I'm looking at how it varies in the x, the spatial dimension in x, right? I would write y equals a cosine kx minus omega t naught, where t naught is whatever moment in time we want to focus our attention on. Now we want to see how the wave varies spatially, right? So we're looking at the same thing as before, except this time it wouldn't be called a velocity, right? Because it's just a delta y over delta x, right? Delta y over delta x. But it's going to behave exactly the same way that this did, right? These things look the same in space as they do in time, yes? And so what would we get? We'd get, this time, the kx, it's a positive value, but when we look at a cosine function, we take that tangent line, it's going downward, right? So it's negative. Get minus a times the k times the sine of kx minus omega t naught, right? Since this is a fixed point, this is kind of like the delta that we had before. It's just a fixed number. It doesn't change or vary. And then we do it again, just like we did here, right? This time we're going to write as delta 2y over delta t squared. X squared. Okay? And this will look like minus a, we'll get the k again, so it'll be k squared times cosine kx minus omega t naught. But this, right, since cosine kx minus omega t naught times a is just what we started with, this is minus k squared times y. Okay? This a shouldn't be there, sorry. The a is in the y. Okay?
All right.
So we have two things that are equal to something times y, right? So let me just summarize that over here. So we've got that delta 2y over delta x squared equals minus k squared times y. And we have the delta squared y over delta t squared equals minus omega squared y. So I can solve both of these for y, okay? And I'll get that y equals minus 1 over k squared times delta 2y over delta x squared, and y is equal to minus 1 over omega squared delta 2y over delta x squared. Since these are equal to the same thing, they're equal to each other, right?
Yeah.
And so what I end up getting is this, minus 1 over k squared delta 2y over delta x squared equals minus 1 over omega squared delta 2y over delta x squared. Yes?
Yeah.
The minus signs will go away. They multiply out, right? And I can find it. I like to write, sorry, this is t. Did I write it correctly here? No. Sorry. There. So I like to always write it like this. I like to write it as delta 2y over delta t squared is equal to, multiply the omega squared times this, I get omega squared over k squared times delta 2y over delta x squared. Yes?
Yeah.
And recall that omega over k was equal to v, the wave velocity, right?
Yeah.
And so I can replace omega squared over k squared with just v squared. And so I get that delta 2y over delta t squared equals v squared times delta 2y over delta x squared. Okay? And this is the wave equation. This term here is like an acceleration, right?
Yeah.
This term over here is like an acceleration, but in the spatial sense, right? So when we do delta y over delta x, we usually call it a gradient, right? And you can think of it as like a steep road, right? You've got delta y over delta x, right? If it's, say, minus 1, that's a pretty steep decline, right? If it's plus 1, that's a pretty steep incline, yes?
Yeah.
So it's called a gradient, right? You've heard of a grade on a road, or maybe a grader, right? That's the big thing that makes roads like level out. But gradient refers to this kind of the slope of the road, right? Unfortunately, there's not a very meaningful term for kind of the rate of change of the grade, right? Or the rate of change of the gradient. I think we call it the Laplacian. I think. Maybe. There's a bunch of terms, but anyways, it's the rate of change of the grade, right? So if the road was, had a steep grade, but it just kept getting steeper and steeper and steeper, right? Then it's like the grade is accelerating as you go farther along, right? So it starts out pretty linear, and then it starts getting steeper, and then steeper and steeper, right, as you move along. Yes?
Yeah.
So it has a rate of change of the grade of the road as you move through, right? So that's what this refers to, okay? And so it's saying that waves, these waves that we are going to talk about, are these things that look in space like they do in time, which is kind of weird, right?
Yeah.
And they're related by this wave velocity v. Okay? And so we'll derive what the wave velocity v is directly for a string in the next lesson, okay? And then we'd be able to write, the wave equation for a string whenever I oscillate a string. But we're not going to derive it for all the other kind of waves, because you've got water waves, sound waves. Okay, the water waves are particularly nasty because it's complicated. But what we will do is we will use dimensional analysis to derive, or at least find a good approximation for the different wave velocities for different types of waves. Okay,
Okay.
including light. So, but we're not going to be able to derive every wave equation that's out there. So, in calculus speak, for anyone watching that knows calculus, right, this is written like this. This would be d2y over dt squared equals v squared d2y over dx squared. Notice it looks very similar to the delta notation that I wrote here, right? We use d, when we write it as little d's, that means that we've taken the limit as the delta approaches 0, okay? And, but it presents differently when you look at it. But I tried to make it look as similar. That way when you do transition over to calculus, you won't be totally unfamiliar with the notation. Is there anything else I want to say about this? Don't think so. You could compare and contrast this with things that are not wave-like. If we have what's called a second derivative in time, right, or an acceleration, is proportional to, if it was not the second derivative in time, but say the first derivative in time, right, is proportional to the second derivative in space, right, of the rate of change of the grade. This would be the kind of behavior you would see for like heat transfer, right? And this is covering energy how energy moves, right? But in the case where there's nothing pulling back, okay? So one of the characteristics of these waves, right, is that there's always something pulling back, okay? And you cannot get that with heat because heat only flows one direction, okay? And so heat transfer obeys a slightly different. It won't have a sinusoidal solution, right? Wave equations always have sinusoidal solutions, okay? Whereas heat would be exponential, right? It would exponentially decay in time as it moves out and spreads itself to the rest of the material. But anyhow, that's getting into the weeds, I think. So this is the form of the wave equation that we'll use, and next time we'll talk about kind of deriving the wave equation from Newton's laws for a string. We can do that, okay? We're going to use F equals ma, and we'll come up with this equation. We'll be able to fill in for what the wave speed is by comparing what we get, applying Newton's laws to this, okay? And we'll say, this is just a wave speed. And then we'll look at some other systems like water waves and kind of reason through what ought to influence the velocity of the wave and use dimensional analysis. Well, basically, what does that mean? It means get the dimensions right? Get the units right. If you're looking for a velocity, you need units of meters per second, right? So we have to find a clever way to manipulate the kind of things that would be important to the wave, right, like the acceleration due to gravity, for example, that might go into it, and to find out what combination we could use to get the wave speed. And it's not an illegitimate way to do it. Actually, Newton used it to derive. Newton used it to explain, I guess, Boyle's law when he was in thermodynamics, which we'll talk about later. So it's commonly used. It's a good way to cheat in physics, by the way. If you know how to derive a physics equation, sometimes you can use dimensional analysis to to get there. But anyways, I digress. All right, any questions?
No.
No? Okay, that's it then.